Hello everyone and welcome back to Common Fluid Problems Part 2. So our next problem is going to be this ball floating in water. And if you already noticed, most of the ball is actually underneath the water line. We're going to say the radius of the ball is 0.8 meters and the mass of the ball is 1,470 kilograms, which seems pretty massive, but keep in mind that water is very dense. So this can be very deceiving just by looking at it. You'll look at this ball is over 1,000 kilograms. There's no way it's going to float. Well, it does. I'm going to prove to you that it does. And along the way, we're going to answer our question, which is going to be this. How much volume of this ball is actually below the surface? Well, to start, given what we have here, we can get the actual volume of the ball itself. So let's do that. Volume is 4/3 pi r cubed for a sphere. Using my radius of 0.8 meters, I get 2.14 meters cubed. Well, if we have mass and we have volume, let's get density of the sphere. Density is mass over volume, 1,470 kilograms over 2.14 meters cubed gives you 687 kilograms meters cubed, which means this definitely has a density less than water, so yes, it will float, even though it is over 1,000 kilograms. So let's actually answer the question. And to do that, I'm going to show you the long way and the shortcut. Either way, what is always a good idea is a force diagram. So I have force Earth on a ball, downward, and force buoyancy, which is upward. I'm going to set that equality right now. Force buoyancy equals force Earth. Well, buoyancy, if you remember, is density of the water, volume of the water displaced times g equals mg, force Earth. Now, if you notice, the first thing that happens is g cancels. I literally want the volume below the surface, which is literally the volume of the water displaced, which is now just mass over density of the water. Mass of the ball, density of the water is going to be 1.47 meters cubed. So this is the volume of the ball that's under the water. If I wanted the volume of the ball above the water line, all I would have to do is take that value and subtract it from this, and that would give me how much of the volume is above the water line. Now, while we're here, there's something I'd like to show you. Let me get a percentage of how much is below the water line. 1.47 meters cubed divided by the total volume. Units cancel. And I get 0.687% below the water line. A little side note, if you go back a bit and remember what specific gravity was, which is a relationship between the density of a material divided by the density of the fluid, which is in this case water. The density of my material, which is the sphere, is 687 kilograms meters cubed over 1,000 kilograms meters cubed. Units cancel, and I get 0.687. So I wanted to show this to you because this is the shortcut. If you get the specific gravity of a substance, which is its density divided by the density of the water, assuming, of course, that that density is less than the density of water, you get a percentage. And if you were to float that object in that fluid, which again, we're using water here, then that is literally the percentage of the object that is beneath the water line. It does not matter what the shape of the object is. That's important because they may give you something with a weird shape, like, say, an iceberg. Now, you may know if you have an iceberg, most of the iceberg is beneath the water. The average density of an iceberg is 916 kilograms over meters cubed. So if we took an iceberg and put it in just regular water, now seawater is actually going to have a different density, but we're just going to say it's the same for simplicity's sake. You would get 0.9167 or 91.67, or about 92% of that iceberg would be below the waterline. So only about 8% of that iceberg would be above the waterline. Again, the density of seawater is slightly different, but the numbers are about equivalent. So the problem for boats is if they're looking at an iceberg, they're only seeing the top part sticking out of the water, and that's about 8% of the iceberg. The other 92% is underneath the waterline, and that is a lot of mass that they definitely do not want to run into. The Titanic, of course, was a perfect example of this. All right, last problem. And this one has almost no math. So here is the question. I have 3 glasses here, all filled to the same line with water. All 3 glasses have the exact same diameter base, and all 3 glasses have a circular base. So if I was to sketch this one, it would look kind of like this, but it's easier to take a look at from the side. So the base of each glass have the same radius, and therefore they also have the same area. However, they have very different shapes. Due to their shapes, you can see A has less water and C has more water. Now the question is going to be this. In which of these glasses is the water exerting a greater force on the bottom of the glass? If we were to put these 3 glasses on a scale, this one would obviously weigh the most and A would obviously weigh the least, but that is not what I'm asking. What I'm asking is which one is exerting the most force on the bottom of the glass. I'm talking about the water on the glass only. Is the answer A, B, C, or other? Feel free to pause it for a second and take a crack at it. Well, the answer is they are all the same. The water is exerting the exact same amount of force on the bottom of each of these glasses. Now, you may ask, Mr. M, but this one has more water. How can the water in A be exerting the exact same amount of force in the bottom of the glass as C if C has more water? Well, I'm going to show it to you using the techniques we have already done in this video, and then I'll do a little side explanation to help you out. For starters, they all have the same atmospheric pressure, so I'm just going to ignore that. Pressure at depth is rho GH. Well, I stated the water's all filled to the same height. So H is the same planet, so G is the same, and I said they're all filled with water. So the density is the same. Therefore, the pressure at the bottom of each glass is the same. Well, let me say, Mr. M, you did not ask about pressure. You asked about force. Well, I also said they have the same area. And taking my pressure equation down here and rearranging, force is pressure times area. We just said same pressure at depth, same area at the bottom of the glass. Therefore, the force on the bottom of each glass is the same. All right, so let me do something that's going to help you a little bit with this mentally. With the equation we just did, this one is probably the easiest to see. Same area top, same area bottom. You have a very obvious fluid column that doesn't change shape. Now this one, I have less water here. So how can the water be exerting a larger force in the bottom of the glass as this one? Well, another way to look at this is it's getting some help from the glass itself. If you look at the way the glass is angled, force normal, the perpendicular force of the glass on the water, is partially downward. So if you need a little mental backing as how the force on the bottom of the glass could be the same as this one, you can think of it as the glass helping out, because there is a downward component to these forces. For cup C, again, the force on the actual bottom of the glass from the water is the same as B. But you may be asking, there is more water in the glass. Well, the sides of the glass, if we're looking at force normal on water, have now an upward component because it's angled upward. So you can think of it as the force on the sides of the glass are actually relieving some of the force on the bottom of the glass here. In other words, just another proof that this pressure equation, pressure at depth, it does not matter what the shape of the container is. The lower you go, the higher the pressure, end of story. The heights are the same, therefore the pressure at the bottom of the glasses is the same. If they have the same area, that means same force from the water on the bottom of the glass. All right, so if you go through this video and the previous one enough times to the point where you really understand these questions, it is pretty much guarantee you to help you on the AP exam or your classroom assessments in the future. All right, I think that is plenty for today. I'm going to close off here. This is Mr. M signing off.